Thank you very much for giving me the opportunity to speak in JuliaCon. In this talk, I'm going to talk about CRRao, a new package, a single API for diverse statistical models. Many statistical models can be trained in Julia, and diversity of the model ecosystem is steadily improving. Drawing inspiration from Zelig package from the R world, the CRRao package gives a simple and consistent API to the end user. The end user faces the fixed cost of getting a hang of this once, and after that, a wide array of models and associated capabilities become available with a consistent syntax under the umbrella of CRRao. We hope others developing statistical models will build within this framework. Let us consider a simple linear regression. So we are considering this empty cars dataset where MPG is miles per gallon, HP is the horsepower of a car, and WT is the weight of the car, and I want to predict miles per gallon as a function of horsepower and weight, plus some error terms where error follows normal 0 sigma square. A likelihood model will follow effectively multivariate normal with alpha naught plus x beta, where alpha here is essentially my beta naught, and x beta will consist of beta 1 and beta 2, and x will consist of HP and weight. So here in this CRRao, we have this simple macro at fit model, which basically models the MPG, follow HP plus weight, and then we have taken this data set, empty cars dataset, from our dataset. So DF contains the empty cars dataset. So you provide the dataset and then you just tell what model class you want to fit. Let's say linear regression. So you just say that, and then if you run this, it will give you the linear regression estimates. So the intercept coefficient estimated, standard error, t-value, p-value, and the 95% confidence intervals, you can get it from here. You can get the BIC of the model. If you want, you can find AIC of the model. You can find R square of the model. So R square is 82.67%. So all standard things are available under CRRao package. Now we did a check of the performance gain, and in R we micro benchmarked exactly same model MPG with HP and weight with this exactly same data set, and it took about 380 microseconds and on an average. And when we did the same thing, we checked with the Julia, it took about 160 microseconds. And then what we did, we also compared it with the Python. In Python there are two packages. One is stat models, which calls the OLS function, and the more popular one is sklearn, which calls the fit function. And very interestingly, we found that stat models is very inefficient. We don't know exactly why it is so, but sklearn is taking about 560 microseconds, whereas R is taking about the LM, which is most popular for fitting a linear regression with stats, is taking about 380 microseconds, and our CRRao's fit model is taking about 160 microseconds. So performance is only one aspect of Julia, as a statistician, I feel strongest feature of Julia is you can write your own code the way you write your mathematical equations, and that becomes very useful when we do Bayesian linear regressions. So if we want to model the Bayesian linear regression with, say, Rich prior, which is also known as conjugate Gaussian prior or equivalent to L2 norm penalty, then all you have to do, just this is your prior. As if it is on my board, I have to write typically that, okay, these are my hyper prior parameters, and V is follow inverse gamma H, sigma follow inverse gamma A0 B0, alpha follow normal distribution with 0 V sigma, and beta follow normal distribution 0 V, and Y follow likelihood multivariate normal with alpha plus x beta comma sigma. Now I write these equations on the board. The advantage is in Julia this code actually works and run. So what we have done in here, that you don't have to even you can do this in Turing. You can literally in the Turing.jl package, you can write the way you write in the board. You can write it in the Julia, and that runs, and that implement the Hamiltonian Monte Carlo or quantum Monte Carlo, and then it gives you the results. For us, what we have done, we have used Turing as under the CRRao. So basically CRRao is calling Turing to implement the Bayesian linear regression. So if you look at everything else is exactly same. So the model is MPG going to fit HP plus weight, with the data frame as the where the data is stored, and linear regression. So if you don't put this is if you just give this much, then what happen is it fits a simple linear regression with OLS method. You see it is fitting a simple linear regression with OLS method. But now if you, instead of just add prior reach, so immediately CRRao would know that, okay, you want to fit Bayesian linear regression and with reach prior, so it will, instead of calling OLS, it will call the Hamiltonian Monte Carlo using Turing, and it will run the model in that way. It took about 0.02 seconds, and now if we run so what we are seeing here is the parameter statistics. Though it has, by default, it has simulated 10,000 samples, Markov chain Monte Carlo samples. These are the posterior mean and the posterior standard deviation, and R hat for all the parameters is very close to 1. So that means the MCMC has been converged, and this is the kind of 95% credible interval for the coefficients and the parameters. And so if you plot the chains, then so you can see that mostly this sigma has converged. I mean, it's nicely, the mixing is very good, and so this is pretty much, and all the beta 1, beta 2 and the alphas, everything is there pretty much. Alright, so then what you can do, you can fit also the lasso penalty on the L1, or sometimes known as the Laplace prior. So Bayesian linear regression with the Laplace prior. So everything will be the same, I'm taking inverse gamma on the scale parameters, and on the coefficient, instead of normal, I'm taking Laplace prior, and rest of the things are pretty much same. So now the changes that you will have, instead of reach prior, you just mention here Laplace prior, and that's it pretty much. Rest of the things will just follow the same way. Plot the Bayesian chain. So it's just like, almost all the chains have converged very nicely. If you go back, you can see that it's actually implements the Turing package. If you can see that, actually it is calling Turing package, and it is actually HMC, Hamiltonian Monte Carlo methods there. They're implementing Hamiltonian Monte Carlo. So the convergence I have seen for even quite complicated model, it's very stable, and Turing is doing fantastic work in terms of fitting Bayesian models, and we are taking full advantage of Turing in CRRao. So you can ask me that if I have Turing, why I should call CRRao. So CRRao is for the people who are not well trained in, say, Bayesian computation, but they are like practitioners, scientists, applied economists, and biostatistician who are not very well versed with the Bayesian computation, who does not want to write their own Bayesian MCMC or HMC. So for them, some standard models are being given. We are going to give them a standard Bayesian models as a part of CRRao. So they just call this fit model, give the model whatever model they want to fit, whatever data set what they have, whatever model class and whatever prior they want to use, just mention that, and rest of the things will follow on its way. So that is what we are thinking in terms of implementing CRRao. But if you have a very specialized model in your mind and you are okay to write down your code, and in Turing, and if you have a very customized model that you want to build, then I think you cannot have better than Turing, because I have spent a lot of time in RStan, and it's oftentimes a nightmare, because effectively it is a 3-language problem, because first you have to have R on your place, then you have to have C on your place, and Stan, and these 3 languages needs to be have the same version. It sometimes, if you have a Windows, you can have a very different kind of problems. If you have a Linux, you can have a very different kind of problems, and and Mac will have a different kinds of problems. So you can face very, very different. When it comes to implementation, RStan works fantastic, but in terms of speed and implementation, but in terms of generic implementation, Stan can be a bit of a nightmare. Compared to that, my experience is Turing is far more seamless, just works like this without any hiccups. So I am very recent convert, I would say, from RStan to Julia Turing, and we are taking the full advantage of Julia Turing in the CRRao. So this is what we are seeing there. Now, what are the list of the models that CRRao can solve? As of now, it can solve linear regression, logistic regression, Poisson regression, and negative binomial regression. For each of these 4 models, we implement the following methods: the likelihood methods, or the often known as frequentist method. Among the Bayesian methods, you can implement reach prior or Gaussian prior equivalent to L2 penalty, Laplace prior or Lasso or L1 penalty, Cauchy prior, T-distributed prior, and uniformly distributed prior. So these are the things as a part of the current capability of CRRao. For example, if you want to fit, say, logistic regression with the logic link, so from the Zelig dataset, we are taking the turnout dataset, and we are just calling fit model. Here is the model, vote as a function of age, race, income, and education. Dataset name is turnout. Here you can see this is the turnout, and we are calling logistic regression with logit link. So if you just run that, and then if you just run that, this here is your fit. So it's this is what you are seeing is just frequentist fit of logistic regression. Now if you want to change your play around with the link function, instead of logit link you can try probit link. So all you have to do, probit, you just write it here, probit, and run it, you get your probit link implementation. If you want Cauchy, you just change it, you get the Cauchy. If you want CLog log, and you get the CLog log implementation. Now if you want to fit the logistic regression with a logit link, so you just mention it here, the same model but with reach prior. All you have to do, just mention reach prior here. Previously, in the previous implementation there was no prior here, no prior, then it will implement a likelihood method. But if you have a prior, it will implement MCMC method immediately. It will identify that problem, and that okay, you are looking to fit a prior, means you are going into the Bayesian version, and it will fit a prior. It might take few seconds, but you can see that first of all I will check for the R hat, and you can see that all R hat are very close to 1, so that means all the coefficients has converged, and you can see the estimates. These are the estimates, and these are the standard deviation of the posterior standard deviation. And if you plot this thing, you can see that all the chain has converged nicely, mixing is very nice. So currently, what are the things that are under development in for CRRao? So right now we are implementing linear discriminant analysis, survival analysis, bootstrap inference, hierarchical Bayesian models, and Gaussian process regression. It is not possible for us to implement this without the great help from Professor Alan Edelman and Viral Shah, and of course a great team is there, Siddhant Chaudhary, Mausam, Ayush, Ajay, and Susan. All of them have contributed to the greatly in from designing the package, from computing from a very basic things, cleaning up, tasting, everything was done as a teamwork. And thank you all, thank you very much.